Okay. Well, I'm pleased to introduce our last talk before lunch, Davide Proment from the University of East Anglia, who will speak on vortex knots in a Bose-Einstein condensate.
Thank you very much. So I should say that I will speak on that work that I've done with Miguel Norato at University of Torino, where I was before, and in collaboration with Carlo Barenghi. So the main results that I will show you today are present in our physical review e-paper. Where's the pointer? Here. But I also want to mention that we were inspired by other works on filament models in superfluids, such as, for example, local induction approximation models or the full Biot-Savart model. And I want just to mention this paper because some of the authors are here in the audience. So just a brief summary about our model and our system that we are considering. What is a Bose-Einstein condensate? So essentially, if you have Bose system that is at very low temperature, you may undergo to Bose-Einstein condensation. So it means that the macroscopic, the great majority of particles are in the lowest energy level of the system. So in this case, you may describe your system with a classical field, which is psi, and you may study the dynamics, and you may see that the dynamics is well modeled by what is called the Gross-Pitayevsky equation. That is nothing but a Schrödinger equation plus a nonlinear term that is essentially due to the interaction between the particles in the condensate. So after suitable rescalings, you may arrive to a non-dimensional equation, Gross-Pitayevsky equation model, and this is what I've used in my numerical simulation and theoretical analysis. So I just also want to mention that there is an important length scale in the system that is called the Healy length, and this length scale tells you when these terms become more important than these other terms. So at length scales smaller than the Healy length, the nonlinear terms becomes more relevant in the equation. The contrary. While at scales larger, it's the opposite. So essentially, this tells you also which is the scale of the vortex that you are observing in your system. I also need to remind you that thanks to the Madden transformation, you can go in a more fluid dynamical framework, and by introducing the real density field and the real phase field instead of working with complex psi field, you may see that essentially this equation describes a compressible in viscid irrotational barotropic fluid. So why this is described as superfluid? Because it's in viscid. And even if the fluid is rotational, you may see some vortex inside your fluid. Why? Because you vortex in this system are singularities of the fluids, and so essentially are all in the density field where the phase change of a multiple of 2 pi. And for that reason, the circulation is then quantized, and that's why we are speaking about quantized vortices in the system. So usually, if you look at experiments or simulations, vortices are or rings or curves that are connected to the boundaries. Okay, so they have simple topology. So our main interest was can we study non-trivial in the sense of topology quantum vortices, so loops. Okay, so knots.
Is that the periodic?
This is, in this simulation was a periodic box, but I mean, you may have similar type of turbulence, even if you're considered reflective, so antiperiodic box. So essentially, what we would like to describe in our system is, for example, a trefoil knot. That is the more trivial knot that you may think about. And so it turns out that it's really a difficult task because, for example, if you're considering just a filament model, it's really easy to describe this knot because you just have to, for example, parameterize your curve and describe the knot in your filament. But when you're working with the Gross-Pitayevsky equation, Gross-Pitayevsky equation is a field that is everywhere in your volume that you are considering. So you're not only working on the core size, but you are working everywhere. And you must also satisfy the fact that around a vortex, the phase must change of a multiple of 2 pi. So our main point where how is it possible to describe the wave function of a trefoil knot or a generic knot, and so how can we set the initial condition if we want, for example, to study the dynamic of this object, and then when you're studying the dynamics, is this object stable, so it will preserve its shapes during the dynamics. So the two ingredients that we have used to describe the wave function of the trefoil knot, for example, in our system, are the following. So first of all, we have, if we think about a two-dimensional condensate, we are able to describe a single vortex that is present in the origin of a two-dimensional condensate very easily analytically. So if we think that this is the origin, we may describe very well the phase. We may describe very well the density, so we are considering axisymmetric density around the vortex point. And we have also a function that is a Padea approximation function to describe the density. And this can be obtained by solving directly the two-dimensional Gross-Pitayevsky equation. So in two dimension, we are able to characterize very well the wave function of a knot that is present, for example, in the origin of the system. And we may also characterize the wave function, for example, of two vortex knots, of two vortex points, by simply superimpose one wave function of a knot, for example, in the origin, plus a wave function of a knot in another point. So superposition in when you are dealing with wave function is the product of two wave function. So this is an approximation. This is not really correct because you're not considering the interaction between the two vortexes. But essentially, this works quite good if the distance between the vortices is greater than the heating length, so the size of your vortex core. So this is the first ingredient. And the second ingredient to build vortex knots is the following. So think that a knot may be built on a torus that have, for example, poloidal radius R0 and toroidal radius R1. So toroidal and toroidal radius. And so a generic knot that I call TPQ is obtained by twisting p times a curve around the toroidal axis and q times around the poloidal axis. So, for example, the trefoil is nothing but T23. Okay. And then you may think that if you take the system in cylindrical coordinate, changing this angle phi, you may select a plane, which I identified here by SOZ, so this plane here. And in this plane, you are just dealing with a wave function that is in two dimensions because it's in a plane. So if you are able to describe the vortex position in this two dimension, you may then consider every angles and work out your three-dimensional wave function. So I'll give you here an example for the triple knot. This is really something similar of what Mark Dennis presented on Monday, I think. The only difference here is that our vortex knot in our system has got some density profile, while in the light knot, I think it's just a singularity. No, okay. By the way,
It's a linear wave equation rather than your non-linear wave.
of course, but this is just the initial condition. I mean, we're not dealing about the dynamic. So it's just the initial wave function that you put. So, so basically, for example, let's have a look at the triple knot. So the triple knot, as I was saying, is the T23 curve. So essentially, it's twisting 2 times around the toroidal axis. So if you cut the torus with a plane, you will see that this gold curve, that is the knot that we want to describe, intersect the planes in 4 points. So in each plane, you have 4 vortices. So your wave function will result as a superposition of 4 2D wave function.
Are the singularities confused? I would think they were in the middle of the red, but they seem to be yellow.
Yeah, I mean, the vortex points are the yellow points.
And there's 4 in the plane.
Yeah, exactly, 4.
Super times 4.
4. Yeah, 4 wave function. And essentially, so you have to control very well and set the position of these 4 vortices to close the curve. So varying the angle phi, you have to move the position of these points. So then, when you go from phi equal to 0 to phi equal to pi, you close your knot. And so essentially, these are the positions that are modeled by R1, that R0, that is the toroidal radius, and R1, that is the poloidal radius. So this one. And you have, I mean, to find a function f of phi that twists your vortex point on the torus, essentially. So, for example, I mean, I don't want to go into the detail, but I mean, if you set up this initial condition with this with S that is essentially gives you the S coordinate with respect to x and y, and alpha, which gives you, in some sense, the position, so it's related to this function f of phi, you are able to describe a generic knot. So you may see that, for example, T23 knot can be described on torus, and the only parameter that you are free to use are the 2 radius of the torus where you build the knot. Okay. This is, I think, very, very similar to the idea that Mark Dennis has by using braids, I think. So once you may build the initial condition in your numerical domain, so this is, for example, for a triple knot that has got knot ratio R1 over R0, so the torus is very, very small, equal to 1/5, or another one, R1 over R0 equal to 2/5, so this one is more bigger, fatter. You may study for, then you may use that for initial condition, and you may study the dynamics, for example, of your knot. So essentially, you may observe that this knot will evolve like a vortex ring. So a vortex ring is moving with a velocity that is parallel to as a axis of symmetry of the ring, and so you may study, I mean, the evolution of this object. Here you see that the object is destroying because I'm considering here to satisfy boundary condition. I'm considering anti-periodic boundary conditions, so reflective boundary conditions. These are art walls. Okay. So this is one type of evolution that you may have, but you may also have. One time, right?
Just a moment or two. It's only 15.
Okay, okay. But you may also have, if you consider different ratio, you may also see some reconnection. So the knot will not be stable, will not preserve its shape. So essentially, by varying the knot ratio, you may study the dynamics of this object. And for example, you may study the velocity of this object by defining in appropriate way the center of mass of this object. So for example, in the case of the trifold knot, we have seen numerically that the velocity of knot, that is measured compared to the velocity of a vortex ring, scales linearly, essentially with the knot ratio. Or for example, we have also studied a little bit the braking mechanism of a trifold knot. So this is quite interesting because we have also always seen a sort of universal mechanism of braking knot dependent on the knot topology. So for example, the trifold knot will always, in our simulation, break into 2 rings by performing 3 simultaneous self-reconnection. Or for example, if we consider the other type of knot T32, this will first perform 2 self-reconnection to produce a first ring, and then we see 2 rings that are linked, and then this will decay in another set of 2 rings by 2 self-reconnection. So, to my conclusion, well, we have developed a technique to write the wave function of a knot in a Bose-Einstein condensate. We have seen that knots essentially propagate as vortex ring, and their velocity depends linearly in our range of simulation on the knot ratio. But we have also seen a sort of, well, some evidence of a universal braking mechanism that we are not able to explain. I think there is a mathematical constraint or something like this, and maybe you may help me to do that. And so the main question now is how to produce knots in real back. So maybe by some phase imprinting using lasers or collisions. So thank you very much.
Any questions or comments?
Do you think there is a configuration of a trefoil knot which would propagate without change of shape?
Honestly, I think that it will decay sooner or after. But I mean, what we have seen is that the more the torus is small, the more the vortex could travel with respect to its size. So I mean, if it preserves its shapes for distance that are much bigger to its size, it's, by the way, an interesting structure that maybe could be observed experimentally. Maybe.
This was
So,
on
I think that-
GP, was it? The simulations were GP.
Yes, well, there are some predictions for LIA system that I think that knots are always unstable. It has been seen that considering the full view of Savart, knots are, well, stability of the knots increase. It is not clear if here we may have some knot that will preserve its shape. Also because the knot when it's evolving is also interacting, producing some Kelvin waves and some sounds. So probably it has a mechanism to decay, producing by some sound and the growth. But I mean, this is an interesting question. We don't have an answer.
So is there any stability results for the ring?
Yeah. I mean, the ring was shown to be stable, I think, by Roberts or somewhat. There's a paper maybe 20 years ago.
As it evolves, it seems to go into 2 circles instead of breaking. Is that part of the evolution equation?
Near the wall.
I mean, it does a reconnection instead of just breaking and falling apart. I mean,
Yeah.
as it's a knot, and then it turns
Yeah.
into a circle.
Yeah.
Why doesn't it just break apart? I mean, is there something in the evolution equation which forces?
So for example, this.
Yeah, I mean, why doesn't it just break?
That's interesting. I mean, and, it's even quite interesting to observe that there are 3 simultaneous software connections. I mean, I could not expect that, but this is interesting. I think that maybe, I don't know, it could be interesting to study the system also when one is studying reconnection event. I mean, I have no idea about that. I just observed that, but you're right. Why is it changed in such a way? Could be interesting to explain.
Okay, well, I hate to cut short an interesting discussion, but we have a very brief period for lunch now. So let's thank our speaker again.